Okay, we're going to begin chapter 7. So this will be lesson 1 of chapter 7. And this lesson will be over none other but the periodic table. So let's begin. And here you have a few pictures of a young bearded Russian dancing the traditional gapak. And this, of course, is in honor of Mr. Mendeleev, who undisputedly is the father of the periodic table, and underappreciated in the Western world, but more about that later. So what do we mean by the table being periodic, or the periodic table being periodic? The term periodic just means that every once in a while, periodically, you have similar properties, and the similar properties are due to similar electron configurations. So this was actually well known for quite a while, and that's how the periodic table began to be put together, is elements with similar properties, both chemical and physical, were placed together. So here, and specifically, elements in the same group will have similar chemical properties. Physical properties vary a little more, as you'll see in the slide, on the next slide, but nonetheless there's definitely what we call periodicity. You can definitely see some trends, some patterns, and that's what we call the periodic table. For example, if you take a look at the density trend, this is a physical trend, but you'll see there's a definite trend. So the most dense elements are actually down here, toward the bottom middle of the periodic table. The lightest ones are kind of on the outside, and then you could definitely see this trend on the periodic table. Even if you put the F block where it belongs in here, you'll still be able to follow this trend. So it's very interesting how this is easily seen if you color code it on the periodic table, which gives the confidence to us that we've arranged it correctly. You can also take a look at the melting point. There is maybe less of a trend, but you definitely see the general character. Least dense elements are again at the far edges of the periodic table. The most dense not the most dense. I'm sorry. The highest melting. The least melting are out here. The highest melting are toward the middle. If you're curious, carbon actually wins the highest melting point of all, and tungsten is a very close second. So if you have not yet respected the element carbon, feel free to begin doing so now. Now, undisputedly, Mr. Dmitry Mendeleev is given credit for the periodic table. In fact, in the Russian language, as well as other languages, it is not called the periodic table, it is called Mendeleevs Table. So the reason his name appears in the books is because he is the one who arranged and listed elements with the same properties. But usually, your fame isn't as high unless you can predict. If your theory can predict future discoveries, then you definitely get into the books. That is how Einstein and all the rest of the scientists made it into the books, and that's exactly what Mendeleev did. He left holes in his periodic table because he said this element has not yet been discovered, however, it'll be discovered. And he gave some properties. He predicted their properties, and for this reason, he is the father of the periodic table. If you take a look, just for one example of this, Mendeleev predicted the discovery of germanium, which occurred later in the 20th century. And here's what he predicted. If you take a look at the atomic weight that he predicted versus eventually the observed atomic weight, very, very close. Density, very close. If you so how about density of the oxide? That's what in the modern language what we call BAM. And so quite a bit of it matches quite a bit, and which is speaks to the genius of Mr. Mendeleev. Another scientist or chemist that's given credit for the periodic table is he improved upon Mendeleev's arrangement a little bit, and instead of arranging elements by atomic masses, as Mendeleev had done, Moseley actually arranged it by atomic number, which is to say increasing number of protons. and this actually rearranged some of the elements, notably at tellurium and iodine. If you take a look at tellurium and iodine in the periodic table, iodine is actually less massive, has a smaller mass than tellurium, but it is listed second in the periodic table because iodine has one more proton than tellurium does. So that's just one example. Mr. Moseley actually died quite young. He actually, I think, was conscripted to go to the First World War, and there we lost a fine young English chemist. So here's kind of an overview of the discovery of the elements. So just some more interesting. The ancients, for example, knew about a number of these elements, most notably gold, copper, silver. Here's gold. Mercury was known by the ancients. Lead appears all over the place, appears in the Bible, for example. Tin was known by the ancients. Carbon was definitely known. Sulfur, brimstone, for example, the word brimstone in the Bible refers to sulfur. And that's from the ancient times. Then there was a big discovery in the Middle Ages. A bunch of these were discovered. And then after that, there was a big discovery session in the 17 to the 1800s. This is where the Enlightenment and our knowledge started increasing pretty quickly. And notice most of these are blue here. A good chunk of the periodic table was discovered. And then later on we began discovering some of the more hidden elements, like the noble gases. Eventually, the 19th century allowed us to discover some of these elements out here, and then in the very end of the or the beginning in the middle and toward our time, we began discovering some of these very heavy elements, and many of these are actually man-made. In fact, there are elements essentially up to here that have been discovered, and most of these elements have been discovered in the nuclear reactors, and none of these really last very long, but we have come up to element 118, Ununoquium, I believe. So a little bit of history about the discovery of these elements. The biggest idea that we want to discuss here is something called periodic trends, and this essentially will show us why and how the periodic table is arranged. So we'll rationalize atomic size, ionic size, something called ionization energy, and electron affinity, and we'll define these as we get to them. So let's begin with something called effective nuclear charge. Now this is not necessarily a trend, but it's something we have to understand in order to understand the trends. So we'll define effective nuclear charge and ZEFF in this way. The effective nuclear charge equals something called Z. This is actually the atomic number or the number of protons. So your Z here is number of protons minus the number of screening electrons, something called the screening number. And this essentially means the number of inner shell electrons. So here you have a valence electron. We can talk about, well, what's the effective nuclear charge of this electron? In other words, how much pull does it feel toward the nucleus? That'll depend on two things: the strength of the nucleus, and then how many electrons screen it from the nucleus. The more screening electrons, the less of a pull it feels. And the stronger the nucleus, the more of a pull it feels. So that's why these two are essentially in the equation. And we're going to treat this equation not quantitatively, not with numbers necessarily, but just in general. I won't really apply too much math to this. It's essentially more of a qualitative understanding, if you would. In fact, let's take a look at what we mean by this. So we've got four elements here: potassium, magnesium, phosphorus. This is rhodium, good old rhodium, and then titanium. And we want to arrange them in order of increasing effective nuclear charge. So we want to put the one first that feels the least attraction to the nucleus, and the one last that feels the most attraction to the nucleus. So let's take a look at the periodic table here, and the elements under consideration again looks like make sure we have these elements before us, and this will make a little more sense, make it a little easier for us to, here they are. So we got ourselves potassium, magnesium, phosphorus, here's rhodium, and titanium. Now, the idea is, if you take a look at the question says the effective nuclear charge of the third shell electrons, the shell for n equals 3, n is the shell number. So this means we're looking at the third shell electrons. Now, some of these, like potassium, for example, has 4 shells opened up. So here's the nucleus, shell 1, shell 2, shell 3, it's got the 4th shell. So we're actually talking about the 4th shell electrons out here. If you take a look at rhodium actually has 5 shells opened up. So rhodium has 1, 2, 3, 4, 5, and we're actually going to talk about its. So it's got 5 shells, but in all of these, we're actually talking about the third shell electron. So we're actually talking about this blue electron. We're actually talking about this blue electron. This is the electron we're talking about for both of these, for actually all these elements. So really, their number of screening electrons will be the same. These number of screening electrons will be the same, and they'll essentially be the electrons below the third shell. So really in the second and the first shell, which has a total of 10 electrons. So both of these have a screening number of 10. Actually, all of these elements have a screening number of 10. So it really comes down to the nuclear charge. And the nuclear charge essentially is wherever they end up, the further along they end up. So now rhodium, for example, has 45 protons. This is its nuclear charge. So really we're going to just arrange them based on their atomic number. Magnesium has the least number of protons, so those electrons are pulled not as strong, or the least. The electrons are pulled the least, with the least strength toward the nucleus. So really, the arrangement is quite simple. The arrangement is actually magnesium, then goes potassium. If you take a look here, magnesium, then goes phosphorus, and then potassium. Then goes phosphorus, then goes potassium, then goes titanium, and then finally rhodium. So this is essentially, you arrange them in order of increasing atomic number, and that's kind of to show that the higher the atomic number, the stronger the nuclear charge. That's the idea. Okay, going on. Next, let's talk about atomic size. And as a definition, atomic size essentially. First of all, let's say one thing here. The reason for the size of the atom is the electron cloud. Remember, the nucleus is extremely tiny in comparison to the gigantic size of the atom itself. Most of this is actually the electron cloud. So the nucleus is quite small. So really, we just care about the electron cloud here. And the atomic radius is defined as 1/2 of the distance between covalently bonded nuclei. All this means is that we're going to measure the distance whenever they're bonded, not as a separate atom. And there are reasons for this, but most substances, most elements exist in the bonded form. You can think of it that way. So in general, the trend is the following. As you go down a group, the atoms become larger and larger and larger. And this is due to the increasing value of n, which essentially means as you go down, you start new energy levels. So if you take a look, this is the first energy level, this is the second, third, fourth. Every time we go down, we start a new energy level. So obviously the new energy level then is further away from the nucleus, which means the atom itself gets bigger and bigger. Now as you go across a period, the atoms actually become smaller. And the reason for this, now hopefully becomes a little more clear, is the effective nuclear charge is increasing. The number of protons is actually increasing, so the nuclear charge is becoming stronger and stronger as you go toward the right, and that's because the number of screening electrons remains constant. So for someone, for example, in the 4th energy level, you get a stronger and stronger and stronger nucleus as you go along, but the number of screening electrons, which is essentially are all the electrons up here, the number of screening electrons remains the same. So that nuclear charge pulls the atom, pulls the electron closer and closer and closer to the nucleus. And I think the next page This one gives a little more of a thorough explanation, and essentially the same thing as we've said. So as n increases, as we go down, as shell number increases, the electron goes further and further away, and so the radius increases. Across a period, it is the effective nuclear charge that increases, and this attraction, the greater effective nuclear charge, makes the electron be attracted and pull closer to the nucleus, so the radius decreases. So this is kind of an overview of the previous slide. If you were to graph, here is where the idea of periodic came from. If you were to graph any one of these trends, you can definitely see if you graph atomic radius, what you find is you find this periodic trend. So we go up and down and up and down and up and down. This is what we mean by periodic. That's why essentially we call the table the periodic table. So what we do is at the top here, what we have is we have the highest radius. So this is actually the beginning of each row in the periodic table. So these three, for example, correspond to, this one is actually lithium, this one corresponds to sodium, and this one here to potassium. So as you'll see, as you go from lithium, and this one then at the end here would be neon. So we're actually going across period 2 from lithium to neon, and in general the radius decreases, and then there's a huge jump as we go from neon up to sodium, and that's because we are creating a new energy level. Sodium is starting a new energy level further from the nucleus, and then the size decreases, and on we go periodically. This portion here is the first time we go through the D block. This is the 3D subshell. This here is the 4D subshell, and here you have you get into the 4F and the 5D. That's why you have so many, but each one of these peaks is an alkali metal. So group 1 metal, essentially. And then each one down here, then it would be a noble gas, if you're curious. These are all noble gases. Okay? So we can now arrange the following in order of increasing size. So we want the smallest to the greatest. Again, if we analyze our periodic table, now let's take a look exactly. It's potassium, sulfur, phosphorus, sulfur, arsenic, and selenium. So if you take a look, it is these 4. So because in general the trend is bigger down and bigger to the left, we know that the biggest one must be AS and the smallest one must be sulfur. And that's the idea. And the best way to remember this is helium is the smallest, and anything closest to helium will be the smallest, then francium is the biggest. So if you remember this, then it's going to be pretty easy. So sulfur is the smallest, arsenic is the biggest. However, the question is, which do we put in the middle first? Who's bigger, phosphorus or selenium? As you go to the right, you get smaller, and as you go up, you get smaller. But however, the difference going from phosphorus to arsenic is much greater than the distance going across this way, because here going up, you're creating a whole new energy level, or going down, you would create an energy level. Going up, you would remove one energy level. So the difference is definitely bigger here. So what we want to do is we want to show as the smallest, we want to increasing, then we'll show sulfur as the smallest, then phosphorus, then selenium, then arsenic. And that's what I believe is what we need to show. So we got sulfur, we got phosphorus, then we got selenium, and then we got arsenic, and then is the biggest of them all. Is the idea. Not too bad. Let's talk a little bit about ionic size, because most of these substances do not exist as atoms, they exist as ions. And in general, cations, and whenever you're discussing this with friends on the weekends, especially, make sure you pronounce it correctly. Please don't go around saying cations. That is very unorthodox, and I would be embarrassed to be around when you call it. Cations is the way to put it. And cations, because a cation essentially is an element or an atom that has lost an electron. By definition, if you lose an electron from the outside, then you become smaller. So if you get yourself an atomic size and an electron is lost, automatically you get smaller. And the reason being is because the rest of the electrons then get pulled closer. Think of it that way. Or you can think that electrons have been removed from the outside, so then they became smaller. And again, it's the effective nuclear charge that has increased. So what you can see here, aluminum is quite small, because here aluminum had lost 3 electrons, the tiniest of them all. You'll see that, we'll talk about anions in just a minute here. Nitrogen will be the biggest. So let's take a look at that. Anions, and again, if a friend says onions, tell them we're not making sandwiches or burgers. We're talking about ionic species here. So in essence, anions will be larger, because then if an atom gains an electron, that electron comes to the outside and becomes bigger, is the idea. So we go from here to here. So it's really the electron-electron repulsion that causes the electrons to spread out. Now, this is an important point. In general, ionic size increases down a group and decreases across the period. And this is exactly the same as atomic size patterns. So in general, you got the smallest ions up here, and then you got the biggest down here. That's the idea. And you can kind of see this. What we have here is, on the left side of this, we have the ion, and on the right side we have the atom. So you'll see, in general, if you take a look at just atomic sizes, notice as we go across a period, we decrease, and then same thing happens to the ion size. And if we go down a group, see, if you go down this way, you'll notice we get bigger and bigger and bigger, same exact pattern as we have on the atomic size. So this is essentially just to show you it's really the same. And if you talk about anions, same idea with anions. As you go down, so F minus is smaller, Cl minus is bigger, and again, that's because we're creating a new energy level. As we go from left to right, we get smaller, both on the atomic and the ionic side. So this essentially shows you that the ionic trend follows the atomic trend. Easy enough. So here is something called the Isoelectronic Series, where the ions have the same number of electrons. And these are actually, what we're doing here, we're actually going across the 3rd period in the periodic table, going this way. So this is period 3. And in each case, we want to make sure we have the same number of electrons. So, and the number of electrons is actually we're going across period 3. Let's make this a little more. Now we're going across period here. This is period 3. And oxygen and fluorine are actually in period 2. This is actually period 2. But the case in point is all of them have the exact same electron configuration as the noble gas neon. If you check the electron configurations, they'll have 10 electrons each. Aluminum, for example, has 13. It lost 3, and that's how you get 10. Oxygen has 8. It gained 2, and that's how it gets 10. So everybody has 10 E's here. And ionic size decreases with increasing nuclear charge, is the idea. So the higher the nuclear charge, the smaller the atom. And in general, that's essentially what we see. So aluminum has the highest nuclear charge of all. It's got 13 protons, plus 13. So aluminum then is the smallest. And the biggest one then must be oxygen, because oxygen has the smallest nuclear charge. If that's a little confusing, don't worry too much about it. Just the major idea here is, again, if the number of electrons is the same, then the number of protons dictate the size. And let's do this quickly, and I think we'll kind of wrap this lesson up here in just a minute. So the question is, arrange the atoms and ions in order of decreasing size. So we want biggest to smallest. Biggest to smallest. So if you take a look at, we got magnesium 2+, calcium 2+, and calcium. So if you take a look, we've got magnesium and we got calcium. So we have both of them we have as a +2, and then we have simple calcium. Well, we know that calcium by itself is bigger than magnesium because it's further down. It has a higher electron energy level opened up. So in general, calcium is going to be bigger than magnesium. If you compare their ions, calcium's ion is going to be bigger than magnesium. So what we'll say is that calcium as an atom, before it lost any electrons, is the biggest of all. So we'll begin with calcium, and then, because calcium is bigger than magnesium in the general trend, it'll also be so in the ionic trend. So we got calcium 2+, then magnesium 2+ is essentially the idea. So not too bad. Actually, wait a minute, I've got my make sure these are oriented the right way. So since we want the decreasing, so biggest to smallest, like so. Take a look at sulfur 2-, chlorine -, potassium +, and calcium 2+. And if you take a look, so we have sulfur 2-, chlorine -, potassium, and there it is. And then potassium + and calcium 2+. What you see, the sulfur is 2-, chlorine is -1, potassium is +1, and calcium is +2. All of them actually have the noble gas configuration of argon. So they have the same number of electrons. So their size then will be dictated by the number of protons in the nucleus. Because calcium has the biggest number of protons, calcium will be the smallest, because the proton charge is the highest, so the electrons will be pulled closer. Therefore, sulfur will be the biggest, because it has the least number of protons. So really, you're now arranging them based on atomic number. So sulfur would be the biggest, then chlorine -, then potassium +, and then calcium 2+ is the smallest of them all. And that wraps up Lesson 1 of Chapter 7. Hope you enjoyed.